bunch of things to go over today. I want to go over the previous homework. I want to go over the current homework. I want to go over the lab that I just graded and gave back to you last night. I want to talk about lab 3, and then we're going to move on to talking about interrupts, which is our next great subject for this course. So, any questions up front? Anything you want to talk about or go over before we get started?
I was a bit concerned with number 34 because I figured I went through the pages and found the status registers and just wasn't quite sure how the picture should be set up.
So this is the one where I asked you to draw the status registers? Yeah, so this is really just it's just to make sure everybody has looked at the status registers in the data sheet. And I mean, you could literally just copy the picture of those 8 bits and you would get credit for it. But the goal was really just to make sure that that you've seen this. So let's take a look at this. Let's go to the full data sheet. I've gotten lazy in life. I don't use indexes anymore. Status register, there we go. So this was the kind of thing I was after, right? But instead of just copying it verbatim, I wanted to read these few paragraphs about this and think about what this is saying. Basically, this is an 8-bit register. The upper 3 bits are unused. Okay, if you try to read them, you'll get zeros. That's what the -0 means, and you can't write them. It has no effect. These other 5 bits are read-writable. They have no particular predefined value, and they correspond to the status of the processor in terms of operations. So this bit is set if a previous operation resulted in a number that was negative. This bit 2 is set if the previous operation resulted in a 0, and so on and so forth. So, you know, any kind of sketch like this is fine, but the real goal was to read through this and try to understand what each of these bits means and ask questions if there's things that aren't clear. And we have not talked about overflow or digit carry, and we'll get to those towards the end of the course. But the main ones you should know about are negative, 0, and to some degree carry, but really negative, 0 are the 2 main ones. And 0 by far being the most important bit. And this is, you know, what we use when we're doing conditional branches, branch of 0, branch of not negative, and so on and so forth. All right, more questions? Sorry?
Sorry, there's a bit of background.
It's okay.
I wasn't quite sure the right way to do 39 and 40. I found a way to do it, it's just that the previous from for it we're using was basically just BZ and BNZ.
Mm-hmm.
0 and not 0. I
Right.
wasn't quite sure which of the branches to use for 39 and 40. I did it, but I did it using the XOR instruction to basically make it so that the comparison to X and Y becomes either 0 or not 0.
Okay, good.
I just feel like there's a way that I was intended to do it. I just did it a different way.
No, that's a perfectly fine way to do it. It's actually a way that you'll see a lot when you're trying to do comparisons. And XOR is a good approach because if 2 things are the same and you take the XOR, you get 0. And if they differ in any other bits and you take the XOR, you'll get non-zero. So that works perfectly fine. The other approach, if you don't like XORs, is to change this to if x minus y is equal to 0. But it's the same thing. In your case, you're going to take x, you're going to XOR it with y, and then if the result is 0, you'll assume that these are equal. In this case, it's almost exactly the same. You take x, you subtract y, and if the result was 0, then it means they were equal. And then from that point, it's just sort of business as usual. So move file register x into the W register, and then subtract the W register, which is x, from y. So this is x minus y, or maybe y minus x. But save the result back in the W register. Otherwise, we're going to change the value of y, which we do not want to do, right? If executing this if statement caused y to change value, you would get your money back on your C compiler, right? So put x into W, subtract y from W, and put the result back in W, not because we care about the value of the result, but just because we don't want to disturb y. And now if it's equal to 0, we want to say z equals z plus 1, so we could say branch if not 0, no increment. Otherwise, increment file register z, and then here's our no increment. So that would code it, but there are, at least half dozen different ways to code this. XORs instead of subtracts. We could do a branch if 0 to a section that increments, and so on and so forth. All right, other questions?
I'd just like some clarification on the last few problems with the disassembly code as far as getting those addresses. I couldn't get those numbers using the PC +2 + 2n, 2n being
43 through 48?
Yeah.
Okay, yeah, let's definitely talk about those. Let me go back to the previous one, though. So a question from someone about why we're putting the value into the W reg. So suppose we do this. Suppose we say move f x comma 0 sub w f y branch if not 0 no inc increment file register z no inc. And suppose initially x is equal to 12 and y is equal to 12. Okay, let's pretend that we're a PIC processor, and let's emulate what the processor is going to do. So we wake up and we find an instruction that says move x into the W register. Okay, so we're going to set the W register equal to the value of x, which is 12. We've done this instruction. Sub WF says subtract the W register from y. Well, that's 12 minus 12 is 0, and put the result back into y. So now I'm going to change y to be 0. And I'm going to say branch if no 0. Well, my 0 bit is set because I got a 0, so I'm going to increment z. And let's suppose z was equal to 5. Now I'm going to increment z to a 6. All right. Well, what's happened? I checked to see if x was equal to y, and it was, so I incremented z. But my poor program that's running now no longer has the same value of y that it had before. I have a program statement here which says if x is equal to y, set z equal to z plus 1. But every time I execute this, my variable y changes value. That's not what this statement is supposed to do. Okay, that is a broken interpretation of this statement. Because y is not my variable, it's the user's variable. I could change it if they said set y equal to something. I can change z, because the code says if this condition is true, increment z. But you can't just change a variable x or y just for convenience, right? You have what's called a side effect. Right? Our goal was to increment z in this case, which we did, but we had the unfortunate side effect of changing the values of other variables in memory that we weren't supposed to change. So the only way to avoid this is by putting this comma 0, so that if x started off at 12 when we subtracted, that 0 went into w, which we don't care about, right? and then we didn't take the branch, we incremented z to 6, but when we're done, x is still 12, y is still 12. So that's the reason for putting the subtraction result into the W register, or the XOR result, or whatever. And you'll see this again and again, right? And I'll usually just comment on it on a test or on a homework by saying, you know, don't change the value of y, or don't have side effects, or things like that. All right, let's talk about the branch instruction. So what is the address in program memory of loop 4? So you can read it up here from the disassembled listing. Loop 4, which is this increment statement, this is at address 56 hex. Okay, you could figure that out yourself. Origin 48 says this increment is going to be at location 48. Goto is going to be at 4A. It takes 4 bytes, so this is going to be at 4E. This is going to be at 5.0. This will be at 5.2. This will be at 5.4. This will be at 5.6. So loop 4 is equal to 5.6. Okay, so the statement in question is when I say branch to loop 4, that got coded as branch 0x56. Okay, why did it code branch loop 4 to branch 0x56? Because loop 4 is a label right in front of the instruction at location 56. Okay, so branch 0x56 makes sense in that respect. But if you look at the data sheet and you say, how do I code up branch 0x56, you start to get into problems. So let me put branch 0x56 over here. And let's look at the coding of this branch instruction. So branch is supposed to be 11010 followed by 11 ends, where n is some number. Okay, so the coding of the instruction is 1101, which is a D, followed by a 0 and then 11 bits, which in the data sheet are written as a number n. Okay, the operation for a branch is described as the contents of the program counter plus 2 times n goes into the program counter. So when we do a branch, when we say branch somewhere, what we're saying is replace the program counter with, instead of the address of the next instruction, whatever address I specify. In this case, loop 4. So our goal is, at the end of the branch, we want the program counter to be equal to 56. But there's some tricks in coding up the branch instructions. So we're told that contents of the program counter plus 2n goes into the program counter. Okay, that's what a branch actually does, depending on what this value of n is. So we have to do some algebra. So the first question is, what's the current value of the program counter? When we're executing the branch statement, the branch is at location 54 hex in the program memory. So the PC is 54. And then we're going to add 2, and we're going to add 2 times n. And that's going to be the new value of the program counter, which we want to be hex 56. So if we're the assembler and we're trying to code this branch 56 instruction, we need to know what the address of this instruction is, which is hex 54. We need to know what address we're trying to branch to, which is 56, and then we need to solve this equation for n. So if we solve this for n, 54 plus 2 is 56 plus 2n. We want that to be equal to 56. Subtract 56 from both sides. 2n should equal 0. N should be equal to 0. So we're going to code this instruction like this. Okay, that's why all of these 11 bits in the coded instruction are 0. And so the hex version of this instruction is D000. And that is what it turned out to be, right? The coding of that branch was D000.
Alright, that clears it up. I was totally misinterpreting the data sheet.
Okay.
I was talking about 2's complement.
Right, so let's look at 2's complement. So let's look at the branch to loop 1. So for loop 1, we have at location 4E in memory, we have loop 1, which says increment file register 80, and then it says branch to loop 1, and that branch is at location 50 in hex. Alright, so I've just copied this from the disassembled listing that I gave you in the homework. So loop 1 is at address 4E, and the branch instruction is at location 50. And again, our branch instruction is going to take the current program counter, add 2 times n, and load that into PC. So the current program counter, which is 50 plus 2 plus 2n, should be equal to the new program counter, which we want to have be equal to 4E. Alright, so again, do some algebra. 50 hex plus 2 is hex 52 plus 2n equals hex 4e. Subtract 52 from both sides. 2n equals hex 4e minus hex 52, which is negative 4. So 2n could be positive if we're branching to somewhere after our current instruction. It could be negative if we're branching somewhere before our current instruction. In this case, we're branching backwards, so 2n turns out to be negative 4 divided out. N should be equal to negative 2. That's why 2n has to be treated as a 2's complement number, because it could be positive or it could be negative. So negative 2 looks like this. This is positive 2. Take the 2's complement. Add 1. That's what negative 2 looks like. And our instruction gets a 11010 in the beginning of it. So here's the coding for our branch to loop 1. And let me just group these into sets of 4 bits. So there's a D, there's a 7, there's an F, and there's an E. So that should be the machine language coding for branch to loop 1, D7FE. Right? Oh, I'm off by 1. Oh, nope, I'm right. That's right there. D7FE. And yeah, I'm not going to grade these questions 43 through 48. These were really, an invitation to look at this description in the data sheet and think about what this means and try to understand it, because every one of these instructions has the same basically same specification, right? Syntax, operands, and then something that describes the operation. Sometimes the operation is pretty straightforward, like a clear file register. It just says 0 goes into the file register. But the branches are probably the most confusing of them because we have this PC plus 2 plus 2n goes into the PC. If we were to do the same for loop 2, right, loop 2 is at address 52 and we're trying to branch to 52. So we would need 52 plus 2 plus 2n equals 52. That basically turns out 2n is negative 2, n is negative 1, which means we're coding up n is negative 1, which is 7ff. And this is a classic example of where looking at the assembly language may not make immediate sense as to why the machine language looks like this. This is why we have assemblers, so we don't usually have to write these ones and zeros ourselves. There's software to do that for us. But we can go to the data sheet and we can think about what the assembly language says and we can translate that into the machine language, and we should be able to do that. Right? And that's always fair game on the exams. Going from assembly language to binary machine code or going back the other direction. So why is this done? Go ahead.
I don't know, I was just going to say that clears up a lot. Thank you.
Okay, cool. So why is this done? Why this business of PC plus 2 plus 2n? The easiest way to do a branch instruction would be just, put in the program counter for where you want to branch to, right? And then you wouldn't have to do any of this foolishness. If you wanted to branch to hex 56, why not just set n to hex 56? And that would work fine on our PIC processor, but on a machine that has 1 million instruction locations, you would need 20 bits to be able to specify one of 1 million locations. And your instruction only has 16 bits and 5 of them are taken for the opcode, so we've only got 11 bits. And for the conditional registers, sometimes we have even smaller space. We only have 8 bits for this branch if not overflow, branch if not 0. This value of n is smaller. So specifying an actual address in memory is not feasible. So these are relative addresses. These are offsets from our current location. That's the first thing that's going on. Branches are relative. That's nice for 2 reasons. One, because we don't need as many bits. We could branch anywhere plus or minus about 128 from our current instruction with an 8-bit specifier. But 2, this also makes your code relocatable. When I have this code here, if I say branch 56, if I code this as saying, branch backwards 2 spots, 1, 2, right? I can put this code anywhere in memory and it'll still work. If I hardwire this and actually in the instruction said branch to 52, and then I move this code somewhere else in memory instead of starting at 48, my branches would break. So branches are nice because they're relocatable and they're small. Why do we add 2 to our PC in this calculation? Because the PC is incremented in the beginning of the instruction execution. When we are executing this increment instruction, which has a PC of 4e, the PC has already been incremented to 50. If we were in the middle of this increment file instruction and we looked at the program counter, it would not be 48, 4e, it would be 50. When this branch instruction starts to execute, the program counter is not 50, it's already been incremented to 52. So that's what the PC plus 2 is addressing. This is the PC of the instruction, the branch itself, but PC plus 2 is actually the value of the program counter when it's executing the branch. The other slight bit of weirdness, go ahead.
Is the adding 2, is that part of the pipeline? Is it just loading the...
It's tied in with the pipeline, yeah. The PC has to be incremented early in the instruction so that we can be fetching the next instruction, exactly. All right, what about the plus 2n? Why do we add 2n instead of n? Because here, you know, I want my change to be -4, where I could just set n to -4, and here I wanted n to be something else. I could just set n to that, right? Why are we multiplying it by 2?
Is it because all the instructions take 2 bytes?
Exactly. All the instructions take 2 bytes, or maybe 4 bytes, but they always take an even number of bytes. So if we simply added n, this low bit would always have to be a 0. Because if our program counter was, you know, 12, it would make no sense to add 3 to that and make the program counter 15, because there's no instruction that starts at 15. It's either 14 or 16. So if we just added n, we'd be wasting a bit. And bits are precious, especially on a RISC architecture. So the designers decided, since this is always going to be an even number, instead of actually specifying that offset, cut it in half and specify what half of it is. And that doubles the range in which you can branch, which is pretty significant. And I mention that because that's another theme you'll see a lot in the coding of these instructions, are these little tricks that you use to increase the functional capabilities of the processor without increasing the amount of hardware you need, without increasing the word size. This is what the access bit does for us. Right? We could use 4 bits and not worry about the access bank, but that would take 4 more bits. So we use a single access bit and we interpret it in these bizarre ways to get more power with fewer bits. On the other hand, question 46, what's the address for top loop? Top loop is location 48 hex. Right, that's the increment instruction following top loop. So when we say go to top loop, right, that got written as go to hex 48. That got encoded as EF24F000. So let's take a look at a go to instruction. And go to has a much simpler operation. We specify 20 bits of a constant. Remember, go to takes 32 bits. So we have 12 bits of opcode, and the other 20 bits are this constant called k. There's the most significant 12 bits of k, and here's the least significant 8 bits of k. So together we get a 20-bit number, and the operation is simply take that 20-bit number, load it into the program counter. So that is, you know, the simplified version of a branch where we just specify the address and it just gets loaded in. But the downside is, you know, because our address could be any of a million different locations, we need 20 bits to specify it. And again, if you look at the operation, k gets loaded into not the entire program counter, but bits 20 through bit 1. It does not change the least significant bit of the program counter. Why? Because again, the least significant bit is always a 0 because the program counter is always even. So if I specify go to and I put 20 ones as the value of k, I'll end up loading the program counter with 20 ones followed by a 0. So the last instruction in memory, which is 2 bytes before the end of memory, which is around 2 million. So that's why the go-to instruction, even though we're going to 48, the constant k was 00024. Right? It's basically the address you want to go to divided by 2. So if you want to mess with that more, right, write yourself some junk code, put in some go-tos, put in some branches, and try to code those things by hand, and then look at this assembly listing. and see if you got it right. All right, so I won't be grading those on the homework, but I wanted to go through them. Other questions? All right, so lab 2 is graded and returned to you. Really good work writing code to do addition. Pretty much everybody got that working, which was fantastic. Couple of general comments. So one comment, we needed to make sure that the code only set the output if the input changed. Right, this is this detail that I said you could leave until the end after you had the addition working. So here's your code to, you know, add 2 numbers, send to port A, and then we go back up to the top. And in the beginning we have some initialization. So up here you want to basically check to see if your input has changed. And if it hasn't, check again, right? And basically sit up here until at least one of your input bits has changed, and then go ahead and do your bit where you pull out the numbers, mask them, add them together, send it to port A. All right, so what does this look like? Typical way to do this is see if port A or port B is equal to, I don't know, I'll make a file register called save B. So is port B equal to save B? And if it's not, then we want to go ahead and we want to start doing our addition. But if it is equal, then we just want to check port B again. As soon as we find that port B is different from our saved value of port B, let's copy port B, the new value, to our save B register. And then go ahead and do your addition code, break your port B into 2 pieces, bit mask, swap, add, send the results to port A, go back up here. And if port B hasn't changed, right, it will be equal to the value of port B that we had here, our save B, right? And we'll just sit here and we'll loop and we'll loop and we'll loop, and as long as port B doesn't change, we're stuck in this loop. Now if even 1 bit of port B changes, we'll see that these are not equal anymore. We'll come out of that loop, copy port B to save B, and go back up to the top. All right, so you needed to have something to that effect in your code. A few people did something like this. Right, so move port B to the W register, subtract the W register from port B, and if the result is 0, go back and wait again. Well, that will work sometimes, but if port B were to change, say right here, you're not going to notice it with this. So let's say port B equals 17. So I'm going to put 17 into W, I'm going to subtract 17 from W, I'm going to get 0, I'm going to go back to my loop. Put port B into W, that's 17 in W, subtract W from port B, 17 minus 17 is 0, I'm going to go back to my loop. Alright, one more time, put port B into W is 17, subtract port B from W, that's 17 minus 17 is 0. And suppose right here, port B changes to, 219. Well, I come back to loop, I move port B into W, that's 219, I subtract W from port B, which is 219, I get 0, I'm going to go back to my loop. So you need some way to preserve the previous value of port B the last time that it changed, so you can see if now the value of port B is different. So doing this outside the loop, either here or down at the bottom, is one way to take care of that. So that's a small detail. It's an algorithmic thing more than a microprocessor thing, but it's something that'll come up. So think about that. The other two main things on the lab. One, remember, for the new experiment, you need to describe the experiment in enough detail so somebody else would know exactly what to do. Right? So you can't just say, write a loop that multiplies two numbers and outputs to port A. Right? Which bits are you going to take in for your inputs? Which bits are you going to use for your output? How many bits are you going to multiply? What are you going to do if the product is bigger than 8 bits? And so on and so forth. And then you need to do the experiment. You need to write the code, you need to load it in, you need to simulate it, you need to talk about your test plan, you need to show the results, you need to list your observations, you need to describe how your algorithm works, you need to put down some conclusions for that experiment, and so on. It's a full-blown experiment. Okay, the new experiment is a lot of work. The other big issue I ran into on a few people's reports was you've got to include your observations. You've got to include screenshots, simulation results, logic timing diagrams, something to demonstrate that your code works. Right? And in most cases, I could look at the code and I could tell this code will work, and a lot of people said, after fixing this last bug, the code worked perfectly. Well, how do you know that? How did you test it? So you come up with a test plan. I'm going to try to add 0 and 0. I'm going to try to add 15 and 15. I'm going to add 7 and 5. Right? Come up with a few tests. Don't just add 0 and 0, because if everything is 0, port B would be 0, port A would be 0. That doesn't tell you that your adder is working, right? So it's a good edge case to test, but try adding this. Try adding that to get some carries in there and get something in your 5th bit. Try adding this to get a single carry, right? Come up with a few test cases and then go through those in the simulation. Grab some screenshots of the variables that you're looking at to show the value of port B and the resulting value of port A, right? Put all that into your lab report. Because remember, you're coming up with an experiment to test, some hypothesis. Your hypothesis is that you can add numbers with a pick. So you design code and a system for doing that, and then you run these experiments, and you're going to put these out there for the world to look at and try to reproduce your results. And if all someone sees is, I ran this and it worked fine, that's like saying, I was trying to invent a new kind of medicine and it worked really well, right? So how can someone quantify that, right? What conditions did you try it under? How did you come up with the determination of it working really well? Same thing here, right? What test cases did you try? So somebody else can try those test cases and confirm that it works, right? And maybe come up with some new test cases that you didn't try to strengthen, the results of your paper. All right, so this is science. Even though it's programming and it's hardware, it's still science. All right, so those are all good to keep in mind for Lab 3, right? Make sure that you have a test plan. Make sure you show the results of testing your code in a way that convinces the reader that your code actually works. And we'll talk about details for that for Lab 3 in a minute. All right, our minute's up. Let's talk about Lab 3. So Lab 3, right, it's our favorite three-way traffic light control system. And we have 3 inputs, right, for the car sensors, west, south, east. We have 9 outputs for the red, green, and yellow lights for west, south, and east. And as usual, east has priority, and then south, and then west. If there's a car to the east light should be green. If there's no car on the east and there's a car to the south light should be green, and so on. And the only real work is what to do when a car with higher priority shows up than the previous highest priority car. So if there's a car sitting to the south and there's nothing to the east, and then a car shows up to the east, what has to happen? The south light has to change to yellow for a few seconds, and then south has to change to red and east has to go green. And if there's a car sitting on the south and the east, and then the car on the east goes away, now south has the highest priority, and so we need to change east to yellow, wait a few seconds, change east to red, and change south to green. So, unless you've done 223 with me, this may be a first instance that you've heard me talk about something called stateful programming. We dealt with state machines in Engineering 250, right? What was the thing about state machines that was unique? State machines didn't always do the same thing for the same inputs. You couldn't make a simple truth table which said for input X, the output is Y. Because the output, the behavior of the machine, depended not only on the inputs, but on the state in which the system was currently sitting. Or put differently, it depended on the value of previous inputs. And all the good stuff in computer science is stateful, right? When I hit the enter key on my laptop, 100 different things could happen. If I'm typing a document, my cursor is going to move down to the next line. If I just type GCC blah blah blah, the compiler is going to start to run. If I'm sitting in a web browser, something else will happen, right? So there's no simple code that says if the enter key is pressed, then do this, right? Depends on the state of the system. Okay, this is going to happen in the traffic light controller. Why? Suppose there's a car to the south and there's no car to the east. What color should the lights be? I don't know. If there's never been a car to the east and this car has been to the south for an hour, then this should be green, this should be red, this should be red. But if there was a car to the east and it just left, then south should be red and east should be yellow. Unless the car left more than 2 seconds ago, in which case east should be red and south should be green. Unless the car to the south just showed up and there had been a car to the west, in which case west should be yellow. Unless south has been here for more than 2 seconds, in which case west should be red and south should be green. So we can't make a simple truth table, which means we can't just make a simple if statement. If there's a car to the east, then make east green and south red and west red, right? We have to understand the state of the system. But it turns out we only need to discriminate between 3 possible states. So you can make a file variable. I'm going to call it state for today, but it's just a file register. And I'm going to give it one of 3 possible values. So state 1 is going to mean east is green. State 2 is going to mean south is green. And state 3 is going to mean west is green. And I'm going to write some pseudo code, and I want to see some pseudo code to go along with your actual machine language, assembly language code for this lab. Okay, pseudo code is higher level code that doesn't deal with bits and tri-state registers and branches and all that kind of stuff. It's higher level. Okay, it describes what you want the processor to do without going into the nitty-gritty details of how. So we're not going to say clear file register or increment file register or things like that. We're going to write in kind of a higher level language. Sometimes it looks like C or Java or something, but it's a pseudo language. It's not a real programming language. It's made to help us organize our thoughts about how this program should work. So here's some pseudo code for the traffic light controller. First thing I'm going to do is initialize the I/O subsystem. That's the ADCON, it's tris A, it's tris B, it's whatever else I want to do. And I'm going to start off with my state equal to 1. I'm going to give east a green light. Actually, I'll start off with 3. I'll give west a green light, because west is lowest priority. So I'll start off with a state equal to 3. And I'm going to set the initial lights. So there's 9 bits you need to set up all your lights. When I say set initial lights, what I'm going to do is set east green to be 1, east red and east yellow to be 0, south green and yellow to be 0, south red to be 1, west green and yellow to be 0, west red to be 1. Okay? You're going to want to come up with some kind of naming convention, some way to specify these things. Use number sign defines maybe. Write things on clean sheets of paper, right? Don't get tangled up in, does this 1 mean west green or west yellow, right? Try to keep those things square. So I'm just going to say I'm going to set up the initial lights based on the fact that I'm in state 3, west should have a green light. So make west green, make south and east red, and make all the other lights off. And then I'm going to go into a loop. So my loop is check car sensors. So let's suppose there's a car from the east. That's the highest priority event. So we've got west, south, east. So if there is a car to the east, what I do depends on what state I'm in. So if state equals 1, I'm just going to go back up to my loop. I don't have to do anything. My east light is already green. I have a car to the east, which means east has priority. East should be green, and it is green. I don't have any work to do. I'm just going to go back up to the top. If the state is equal to 2, that means south has green. So what do I have to do? Set the south to yellow. Wait for 2 seconds. That's just your delay function from the code that's already provided. And then set south to red. Set east to green. Change your state to 1 and go back up to the top. Alright, so this is all if there's a car on the east. If I'm already got my east green light, nothing to do. If south currently has a green light, change south to yellow, wait 2 seconds, then change south to red, change east to green, set my state to 1 to show that east is green, go back up at the top of my loop. Otherwise, my state must be 3, so set west to yellow. Wait 2 seconds. Set west to red. Set east to green. Set state equal to 1, go back up to the top. Okay, that's the whole processing if there's a car to the east. I'm going to need another chunk of code which says if there's no car to the east, but there is a car to the south, what do I do? Well, if my state is already 2, I don't have to do anything. If my state is 3, then I have to set west to yellow, wait 2 seconds, set west to red, set south to green, change my state to 2. If I'm in state 2, if there's a car to the south but I'm in state 1, I don't do anything. Right, because that means that east is green. Oh, sorry. If there's no car to the east but there is a car to the south and I'm in state 1, then same thing, right? Set east to red, wait to yellow, wait 2 seconds, set east to red, set south to green, change your state to 2. So you've got 9 sort of conditions to deal with, right? Depending on what state you're in and whether there's a car to the east or to the south and not to the east, or to the west and not to the south or the east. And you can just start writing this code, but if you think about it for a while, you can make this a lot slimmer, right? There's enough parallel structure to what you're doing in each case that you can streamline this. You know how to do call and return, right? You can nest up to 31 calls. Take advantage of that. Write yourself some functions. If you've done CSE 224, modularization, right? Break functions up into things that you just call. For example, set south to yellow, wait 2 seconds, set it to red, set east to green. Set west to yellow, wait 2 seconds, set it to red, set east to green, right? Those are almost exactly the same thing. You can make a function, just call it yellow, call yellow, and have yellow basically look to see what state you're in, set the corresponding light to yellow, wait 2 seconds, and then set that light to red. You can bundle that all into one function that you just call and return. Your delay for 2 seconds, right, that's already a delay routine that can be called, and you can just hardwire in the top of that, loading a magic number like 20 into the decount file register, and then doing that inner loop. Okay, but that's an idea of an algorithm, right? So do some initialization, set an initial state, set your initial lights, and then explore these cases. And how do you set south to yellow or set south to red? Well, if you look at the description of the lights, it's mostly port B with 1 extra bit for port A. So really, if I want to set, west to green and south to red and east to red, I just have to load in a particular 8-bit pattern for port B. And if I want east to be red, I can just do a bit set file port A, 7. Just set that bit directly. So it's a fair amount of typing, but it's not terribly deep. Okay. But you really want to figure it out on paper before you start coding. Because once you're coding and you've got and LW and branch if not 0 and all this kind of stuff, it's really hard to debug your algorithm at that point. So you write pseudocode to work out the algorithm. And once you've got this working, you go through it on paper, you try some test cases, you convince yourself that this works, then you're just translating this into assembly language. And if something's not working in your tests, presumably it's a problem with how this got translated. So now you run the debugger, you go through your assembly language program, while on paper you're going through your algorithm. And here I say if state equals 2, set south to yellow, but in my program, state's equal to 2, but west is getting set to yellow. Okay, something went wrong with how I translated this into assembly language. You know right where the bug is now. Can't do that unless you know that your pseudocode is working correctly and your pseudocode exists, right? So write this first, debug this first on paper. Once you're totally convinced that this is correct, then start coding it into assembly language. Okay, how do you demonstrate this? Make a test plan. I'm going to start off with no cars present, then I'm going to put a car on the east, and then on the south, and then on the west. And the east light should be green, everything else should be red. And then I'm going to take away the car from the east, and east should go yellow, and then red, and south should turn green. And I'm going to take away the south, and south should turn yellow, and then red, and west should turn green. And then I'll put a car back to the east, and, you know, etc. There's a lot of different states here, right? I don't expect you to test every single possible state, but you got to do more than 2 or 3. Okay, you want to know that you're handling the priorities correctly. You want to know that when a car arrives, yellow light transitions happen correctly. You want to know that when a car leaves, transitions happen correctly. You want to know that when a car leaves where nothing's supposed to change, nothing changes. If there's a car to the east and a west, and the west car disappears, nothing should change. Because west had a red light, and if the car goes away, the light should just stay red. So if things start going yellow and so on, then you've got a problem in the algorithm. So come up with a set of tests that you're going to run, and then go through the simulator and put in some breakpoints and document this, right? So you at least, at the minimum, want to be showing the values of port A and port B in your list of variables. And, you know, so here we have cars sitting at all 3 lanes. As you can see, you know, this light's green and these are red. And show me what those variables are in the simulator window. And then say, now we're taking away the car to the east, which means port B is changing, port A is changing to such and such. Here you can see from port B that there's a yellow light to the east. Right, and show me that window. And then, you know, a few steps later, the east turns red and south turns green, as you can see in this, you know, value of port B, right? So talk the reader through how you convinced yourself that this code is working, okay? This is going to take at least as much work as actually writing the code itself, depending on how fluent you are with working with MPLAB and the debugger. Okay, but it's a really important skill to get good with, is being able to work with this stuff down at this instruction by instruction debugging level. Okay, so this is really good practice. All right, questions about any of that?
Can you go over the wait 2 seconds for that's provided in the lab?
Yeah, so
Yes, it's like step by step of it, if you can.
yeah, so we played with this some on Tuesday. It's all happening down here, right? And the first piece is this interdelay, right, which basically loads 195 in the W register, and this inner loop decrements it, and if the result is not 0, goes back to interdelay. So these 3 instructions get executed 195 times, okay, because W will decrement from 195 to 194 all the way down to 0, and when it gets to 0, it will not take this branch. So these 4 instructions happen 195 times. That's 195 times 4, and each instruction takes 128 microseconds, so that's 100,000 microseconds, which is 1/10 of a second. So if you come to this interdelay, right, if you call delay from there down to this statement after the branch of not 0 will be 1/10 of a second. Okay, that's just our spin our wheels for a while delay loop. And before you call this, you're supposed to load a value into decount, which is how many tenths of a second you want to wait. So the sample code loads a 20 into decount, which says wait for 20 tenths of a second. That's 2 seconds. So how does that work? Well, we call delay, we wait 1/10 of a second, we come down here, we decrement decount. It was 20, now it's 19. If that's not 0, we jump back up to delay and we do the whole thing again. Wait another 1/10 of a second, decrement decount. Now it's 18. Wait another 1/10, decrement decount. Now it's 17. We're going to do that 20 times. The 20th time decount was 1. When we decremented it, it became 0. This branch, if not 0, does not happen, and so we execute the return. So the whole time
So-
from... Go ahead.
Yeah, so the loop statement and then the inner delay, are those two functions, those are just basically just waiting 2 seconds.
Yeah, so inner delay is waiting 1/10 of a second.
Yeah, and after the 195 goes back down to 0, then the 20 gets decremented.
Then the 20 gets decremented.
Okay.
So anytime that you say call delay, you won't return from delay until a certain amount of time has passed. How much time, whatever value you put in decount, that many tenths of a second. So if you want a 2-second delay, put 20 into decount, call delay. 2 seconds later, you'll come to the next instruction.
Okay, and so if you want like just 1 second, you would just move the 20 into a 10.
Yep, exactly.
Okay, that makes more sense.
Okay, cool. So I'm not too worried about the timing. I showed you how to use a stopwatch function in MPLab last time. You can use that to double check the stuff, because single stepping this, 195 times 20 is kind of annoying, right? And I don't expect you to demonstrate that. If you want to show the timing using the stopwatch between, the call to delay and the branch, so put a breakpoint here, put a breakpoint here. Again, you'll see it's about 15.6 milliseconds according to MPLab. But I'm guessing most of you are just going to use this code verbatim, right? And as long as it's commented, that this is supposed to do a 2-second delay, I'll look at that code, I'll be able to tell that that works. So I'm not real worried about demonstrating the timing, okay? But I do want to see the values of port A and port B that clearly show, the lights, one light green and then the green light yellow and then a different light green and the other light's red for each of the transitions of the car sensors. If that makes sense.
So, I feel like I have a good idea on how to program states for the traffic lights.
Okay.
I'm just a bit confused on how basically the program needs to respond to the states of if there's a car, and I'm just not sure how to program it to respond to things like that, to respond to if there's something there.
Right.
Namely, I'm also having a bit of trouble with figuring out how to basically make it so that I can change inputs mid-run.
You mean for testing it?
Yeah, because there should be a state for if there's one car in each of the 3 lanes, if there's a car in all 3 lanes, if there's a car in two specific lanes, I should be able to have an input ready for each of those circumstances.
Right, so you can use the regular stimulus option in the simulator, in the debugger. Right, set up a stimulus for setting RA0 high, set up one for making it low, set up a pair for RA1 and a pair for RA2.
Right, I could link.
And that will let you go ahead and set the inputs high or low for those 3 sensors.
RA, I could make those inputs represent the states of the cars.
Yeah, RA0 represents that there's a car to the west. RA1 tells you if there's a car to the south. RA2 tells you if there's a car to the east.
I see.
So set up stimuli to control the values of those 3 pins, and then you can model whatever condition you like.
Yeah.
Once you have all of this working and you're pretty convinced of it, right? This is a reasonable one to throw into the GUI. So I wrote this up this morning. So here's my 3 car sensors for west, south, and east. and I've got a guide in front of me. This is basically the eastern red, yellow, green. This is southern red, yellow, green, and this is western red, yellow, green. So west has a green light right now because there's no cars anywhere. If a car shows up to the west, nothing happens. But if a car comes to the south, that turns yellow, and then turns red, and then south turns green. And if that car goes away from the south, then south turns yellow, and then it'll turn red, and west will turn green again. And if a car shows up to the east, then that turns yellow, and then it'll go to red, and then the east will turn green, and so on. So again, this won't help you debugging, but you can use this once you're pretty sure everything is working to kind of double check more visually than looking at port values, and it's a little easier to change the values using this. Maybe not. Alright, so no, I don't expect you to go through all possible situations because I guess there's 8 possible placements of cars being present or not, and for each of those there's 3 possible things that can happen, so that would be 24 tests, and I don't expect you to do all of that. But you know, have a car with lower priority show up, have a car with higher priority show up, have a higher leave, have a lower leave, you know. 5 or 6 test cases is probably enough to do enough that you know, it demonstrates that this code is probably working. There could be some weird edge case, like if there's a car to the south and the west, and then a car shows up to the east, something glitchy happens, right? But try to catch, you know, a few basic cases. All right, other questions? All right, let's do about a 3-minute break, and we'll come back. I'll talk about the homework, the new homework, and then I'll start talking about interrupts, which will be our next topic. So come back in about 3 minutes.